this is the second set of past exam questions I gave you as a little bit of holiday homework. And so we're not going through this whole exam because we haven't yet done the whole course, but I've picked ones for you that you're able to do. So I think we're doing questions 1, 2, and 6 and 7, I think. So let's take a look and see where we get to with these. Okay, here we go. The first one is Poisson distribution, so we should be able to do this one. Random variable x has a distribution lambda 31, and we're using a normal approximation, so we've got to change that, and we're trying to find this. Okay, so when you're doing a normal approximation, so I guess we can first of all say, well, it's going to be approximately normal. I always just put approx there. I don't think you have to. You don't need to. It's going to be 31, 31. Because remember, with the Poisson distribution, the variance and the mean are the same. So this will be our approximate. Now, of course, when we're going from Poisson, which is discrete, to normal, which is continuous, we need to do a continuity correction. So what we're trying to do here is probably that x is greater than, now 40 has a range from 39.5 to 40.5, so we don't want 40 in our in what we're doing, so we're going to, when we turn it to normal, it's going to be 40.5, so we want it to be greater than 40.5, and now we're going to do our standard normal, so we switch this to a z value. We're going to have 40.5. We're going to subtract our mean, and we're going to put that over the square root of our variance. Now, when you chuck that into your calculator, you'll have z is greater than 1.706. And so, you know, if you're thinking about your normal distribution curve, it's going to look something like this. Here's our mean. And let's say 1.7 is over here, 706. You want this bit here, so that will be equal to 1 minus phi 1.706. Now, I'm pretty sure you guys are all capable of using the standard the z tables. So you should be able to go along here, 1.7. And then go across and find out what 6 is. So I think in this case it looks like, oh, I can't see, it's not scrolling very easily. Maybe it's a 5. So it'd be 0.9559 maybe. Okay, 0.9559. So it should be 1 minus 0.9559. So we do that. Hopefully I read that off right. And then we get 0.441. Okay, it's 0.0. Sorry, my mistake. I misread my calculator there. 0.441. Okay, so that's the first question. So sorry, that's gone a bit skew-iff there. All right. The next one, the airline finds out that on average 1 in 100 passengers do not arrive for each flight. It randomly occurs for one particular flight. Always sells 403 seats. The plane only has room for 400 passengers. Okay, so the flight is overbooked if the number of passengers who do not arrive is less than 3. So we're going to use a suitable approximation to find the probability that the flight is overbooked. Okay, so first of all, I hope you can see this as a binomial. We're going to do the approximation in a minute, but this is a binomial, and there's 403 seats that have been sold, and the probability of someone not arriving is 0.01 or 1 in 100, right? That's the distribution. But we can approximate this to Poisson. So we're just going to go 403 times 0.01, which will give us 4.03, or 1% of 403, right? 4.03. So that's what we have. And the flight is overbooked if the number of passengers who do not arrive is less than 3. So in other words, the probability that X is less than 3. So if it's less than 3, in this case with Poisson, we're going to go e to the negative 4.03, so because that's our lambda, right? Then we're going to go into 1. That's a probability of 0 missing the flight. Then 1 missing the flight, and then 2 missing the flight, over 2 factorial. Okay, and when you plug this into your calculator, you should be getting 0.234. Okay, so that's question 2 done. The next one that I've got for you is question 6. So we'll scroll down to question 6. Okay, this is a linear combinations of variables question. Okay, so the numbers of barrels of oil in millions extracted per day in 2 oil fields A and B are modeled by the independent random variables X and Y. So I guess we can say that one belongs to A, and B is this one here. They're normally distributed. Now, the income generated from the oil fields is 90 per barrel for A and 95 per barrel for B. We're going to find the mean and the variance in daily income of millions of dollars generated by field A. Okay. So the daily income per barrel is like this. So what we're in effect trying to, we've got 90x, right? 90 times the number of barrels of oil sold. So what we'll do is we'll find the mean of that, and so that should be the 3.2, which is the number of barrels of oil, millions, extracted per day, the average, 3.2 million, and then each barrel of oil is $90. So therefore, the mean daily income is going to be 288 million mean income. And the variance, is it variance we want? Yep, it is variance. So the variance of this 90x is going to be 0.4, which is, as you see here, this variance squared, right, because that's the variance there. And then we're going to times it by 90 squared to get 1296. All right, so that's part 1. Now, what I might do is I'm probably going to need this information here. So I will pull it down to part 2. I don't know why they gave us so much. Okay, so so that we can refer back to what it says there without having to scroll up and down, I've brought that down. Now, for the second part, we're finding the probability that the total income is at least 670 million. Okay, so how do we work out the total income? Well, this is going to be 90x plus 95y. Okay, now 90x, that's the $90 per barrel for A. The 95 comes from here, which is the cost per barrel for B. Now, this is going to be normal, a normal distribution, isn't it? Because because they're both normal, when we add two normals together, it'll be still normally distributed. Okay, now we've just got to find out what these two, the mean and the standard deviation, are. Now the mean will be E, so EX will be what we found in the previous one, so 90 times 3.2, I think we already got that, didn't we? Plus the mean of the second one, which is 95 times 4.3. Now we put that all together and we get 696.5. 696.5. So children coming in and out at the moment. A bit distracting. Okay, now the variance. Oh, sorry, just going back here, I've made a mistake. That's not this here. 90x plus 95y should have been in there, right? Okay, now there, and this will be 90x plus 95y, is going to be equal to 0.4 squared times 90 squared, which I think we did up above in the first question, didn't we? Yeah, we did. But then we're going to have to add in the variance of the second field, B, which is 0.6 squared over here. But then because it's 95 per barrel, we've got to times that by 95 squared. When we pop all of these together, we get 4,545. So now we're ready to do our probability, now that we've got these two values. So this here is this here, and this here is this here. Okay, so the probability that 90x plus 95y is at least greater than 670 million. Okay, and then we can turn that into is equal to the probability, we'll use standard normal distribution, z is greater than 670 is our value, but we're going to take away the mean, which we found to be 696.5, and then we're going to pop it over the variance, which we just worked out to be 4545, which is equal to the probability that z is greater than negative 0.393. Now, if we were to sketch out our standard normal curve, gee, that's atrocious. Just pretend it's not atrocious. Here's our mean. Negative 0.393 is there, and we want greater than that, so we're wanting this bit here. So that's equal to phi 0.393. And so we just read that off our Z table, and we should get 0.653 for that one. I hope that's making sense. What else do we have? Is that it? Question 7, I think, was the last one, wasn't it? Question 7. Question 7. Here we go. Question 7. So, in the past, the number of cars sold per day at a showroom has been modelled by a random variable with distribution PO 0.7. Following the advertising campaign, it's hoped that the mean number of sales per day will increase. Okay, so we want a mean number of days, right. In order to test, okay, so straight away, we know hypothesis testing, we've got a 10% significance level. The total number of sales during the first 5 days are noted. You should assume Poisson model is still appropriate. Okay, so let's write down what we do know. We know that X is Poisson distribution, 0.7. But that's per day, isn't it? And we're looking at 5 days, so we can make it Poisson, we times 0.7 by 5, 5 7s are 35, so 3.5. Okay, now they're hoping that the sales will increase. So we start off with what the sales are as our null hypothesis. The sales are lambda equals 3.5, and the alternative hypothesis is that we're increasing the sales, so lambda is greater than 3.5. And this is obviously one-tailed test because of this sign here. It's not equal. It's not equal to. It's greater than. So that means that we're cutting off the right-hand side of the distribution. So we're that the top 10% will be rejected and said that it doesn't. Will say that it doesn't belong to this distribution of Poisson 3.5. Okay, so that's what we're going to do, and we've noted after 5 days we've carried out the test. We've got 5. So 5 cars were sold. So let's say, what's the probability that X is greater than or equal to 5? And we'll see what percentage of this distribution would give you 5 or more sold in the 5 days. And we do that by going 1 and we take away 0 to 4. So e to the negative 3.5. 0 cars sold. 1 car sold. 2 cars sold. 3 cars sold. 4 cars sold. Right. Then we chuck this into our calculator. So in effect, what we're doing is we're finding out the probability here of 0, 1, 2, 3, or 4 cars being sold. And then we're subtracting that from 1 to find out what's the probability of more than that being sold. Now, when you do this, I was getting 0.275. Okay, so at this point, we now have got to do a comparison. 0.275, we compare it to our significance level, which is 0.1. And you can see that that's greater than 10%. It's actually 27.5%. So we can now make a judgment. Since it's greater than, there is no or not sufficient evidence to suggest sales have increased at the 10% significance level. Right, and that would be that. Now we've got one more part to the story. One more part. Okay. Oh, goodness gracious me. Okay, fine, that'll do. The number of cars sold per day at another showroom is Poisson 0.6. Assume that the distribution for the first showroom is still Poisson 7. Okay, find the probability that the total number of cars sold in the 2 showrooms during 3 days is exactly 0.2. Okay, now remember, both these numbers here are for 1 day. So we need to turn them into 2 days. So this Poisson 0.6 over 2 days becomes Poisson, we'll call this one Y, is 1.2. Hang on. But we want to do 3 days, don't we? 3 days, so it should be 1.8 3 times. I don't know why I said 2 days. Oh, 2 showrooms. 3 days, right? And the other one is Poisson. This was from the previous part of the question. Is Poisson 0.7. and we'll call this x, that will become, in 3 days, that will become 2.1. Now what we're doing is the total number of cars, so we're going x plus y, and we can say this is also Poisson, we're just adding, so that works nicely. And over 3 days, we add those, we're just going to add 1.8 plus 2.1. So x plus y is Poisson distribution with 3.9. Now that we've got our distribution, we can find the probability that the number of cars sold is exactly 2. So what is the probability that x plus y equals to 2? And that's very easy. It's e to the negative 3.9 times, now, 3.9 squared over 2 factorial, which is equal to 0.154. And that should be it. I think that's all I've given you for homework. I hope that helps. Let me know if you've got any specific questions that I haven't answered in these videos. Very happy to help. Enjoy the rest of the holidays.